Okay, good afternoon, everyone. Today's Taos seminar speaker is Jeff Snyder, who I'm very happy to be joining us today from Oklahoma. So Jeff is, I'll tell you a little bit about Jeff. Jeff is currently a research meteorologist at the National Severe Storms Lab in Norman. Before that, he spent a lot of time in Oklahoma. He got all 3 degrees at the University of Oklahoma and the School of Meteorology. His graduate degrees were in the same research group as me, so we shared an office for many, many years. So he got his master's and PhD under the advisement of Howie Bluestein. After that, Jeff worked as a graduate student collecting data with mobile radars on supercells and tornadoes, and worked on various projects for his graduate degrees, including more radar conceptual projects like attenuation correction, and then more sort of physical-based dynamic studies of supercells for his PhD. After that, he was an NRC postdoc, is that right?
That's correct, yeah.
Yeah, so
where we also shared an office.
Yes, that's right. We overlapped as NRC postdocs at the National Severe Storms Lab for a year before I was lucky enough to come here. Jeff moved on to become a research scientist at the Co-op Institute that's affiliated with OU and NSSL, which was then known as SIMS, is now known as CRO. And that was until 2017, after which he very deservedly started a federal position at the National Severe Storms Lab, where he's, as I mentioned before, currently a research meteorologist and the team lead for the Doppler radar and remote sensing research. So that's in the Radar and Research Development Division at NSSL, for those of you familiar with it. So Jeff has worked on a lot of projects and has a pretty big breadth of topics. That includes supercells and tornadoes, observations and dynamics. That also includes a lot of radar application type work. And as I mentioned before, attenuation correction. He's done hydrometeor classification type work. And that's not even what he's going to talk about today. He's going to talk about hail, which is also something that Jeff's increasingly been working on. And so I mentioned this a few weeks ago. I'm very excited to have Jeff give this talk. I don't think we've had really a hail-related talk at least since I've been here. So Jeff's going to talk about novel hail observations and work being done at NSSL to improve detection. And I'm looking forward to this. There's a lot of feelings in the community about whether we can use radar to detect hail very well, or even hail size very well. So I'm looking forward to see what Jeff has to say about it. So Jeff, take it away.
Thank you, Mike. I appreciate the very kind words, the nice introduction. As Mike stated, we've known each other for quite a while. I entered grad school in 2005 and moved right in with his office, and then similarly followed him through postdoc, where he had to, I'm sure, overhear my wonderful music selection that probably doesn't overlap with his preferred music selection very much. But yeah, I'm happy to spend the next 40, 50-ish minutes talking about some of the hail work that we're doing here in Norman, and more specifically at the National Severe Storms laboratory here. So a lot of what we know about severe weather, the distribution, the sizes, intensities, et cetera, are driven by reports. So at least in the US, that drives almost the entirety of what we know about our severe weather climatology. The reports are usually provided by individual country governments, or they're organized that way. So in Europe, there's a European severe weather database. In the United States, we have what used to be called storm data. Now it's the storm events database. hosted on the East Coast, but basically all these individual reports come into local National Weather Service forecast offices, get compiled, and then submitted to the national database. Most of the reports for hail, for tornadoes, wind, flooding, blizzard, etc., come from the general public. They come from storm spotters or chasers, law enforcement, emergency management, etc. And a lot of times the law enforcement and emergency management are forwarding calls that they get through 911 from the general public and from others. One of the issues, of course, is that a lot of times the reports are just estimates. They're relayed by phone, radio. We get increasingly more use of our smartphone apps and computer applications, things like MPing. That's relatively easy to use on the phone that can end up at the National Weather Service forecast offices, as well as an increasing amount through social media. So we're getting more reports, but a lot of those don't necessarily end up in any official database. We also have scientific field campaigns, and these can provide a more focused, much more dense collection of actual observations, actual measurements. So they typically are more accurate and more precise. But of course, they cover a much smaller spatial temporal region. So we only get them where these individual field projects are taking place. And we use those then to try to generalize some of the patterns that we see, either looking at relationships between hail sizes, for example, and radar data or satellite data, or using that to inform some of the numerical modeling that we have. So in terms of observing and detecting severe hazards, again, a lot of this will focus on, which I'll get to in the second half of the presentation, this high-speed imager that we're using now, but just in a broader context, or to place those more novel new observations within the broader historical context. A lot of the eyewitness reports, in situ measurements, weather radar, all that is used to collect observations or to study the phenomena that we want to study. In this case, it's hail growth and melting, other microphysical processes before it hits the ground. To a much lesser extent, we can use satellite and lightning data. There's some correlations there in some studies, but I'll focus mainly on weather radar. I know Stony Brook has a robust radar program, so presumably a lot of us in this meeting have some general understanding of how radar works, but with the use of especially polarimetric radar, we get a lot of additional information. And the WSR 880, the nationwide NWS operational radar network, has been essentially in place now solidly for about a decade. And we're getting a lot of really great data from that. And from that, we're able to develop correlations and really study the structure of individual hailstorms, as well as really get into the nitty-gritty of individual hailstones. But of course, most modern weather radars, especially polarimetric radars, give us Doppler velocity, precipitation intensity, and that could come from products such as differential, specific differential phase, or reflectivity based, or there's other combinations of radar parameters that give us some estimate on rainfall rate and rainfall accumulation. It's also very good at discriminating different types of hydrometeors. So we can use it really well. I mean, most relevant to where I'm sitting here, which was within a mile of a tornado track a couple of days ago. We can pick out tornado debris really well. We can also use the radar to help us identify where hail is falling and some of the characteristics of that hail, and where it's not falling. So where we have light rain, heavy rain, hail mixtures, pure hail, etc. Radars also have the advantage of being able to remotely sample a very large volume relatively quickly. So depending on the specific radars, we can sample most of the atmosphere within a 50 to 250 kilometer radius around the radar, and somewhere on the order of 1 to 10 minutes. Of course, again, it depends on the specific radar being used. But in the case of the WSR 880, we're getting volume updates on the order of 5, 6, 7 minutes. So mid single digits. There's other research radars such as RAXPOL that can give us much faster updates, and certainly other experimental radars in development that rely on or that are able to leverage phased array radar technology that can give us volume updates on the order of about 10 seconds. So just in terms of turning more specifically to hail, a lot of, again, what we know from a climatology standpoint, and that kind of informs some of the studies when we look at the relationships between radar parameters or satellite structures and hail, come from these reports, and most of them are just the max hail size. So we don't really get any information on the size distribution. A lot of times hail, of course, falls in a somewhat smooth distribution of sizes, inverse exponential, or there's other shapes of the particle size distribution. We have very coarse resolution, both in time and space. A lot of times the reports are highly quantized. And again, they're generally point observations, when in reality, this is a somewhat continuous, somewhat smooth swath. So hail doesn't really just fall at one location at one time, which is what a hail report would show. A storm will produce hail over the course of minutes, sometimes hours, but oftentimes there's an unsteady nature to the production and fallout of hail. And of course, again, we get multiple kind of a smooth range of sizes, whereas the report database would indicate that we just kind of get these significant groupings of hail size, often around coins or golf ball, baseball, et cetera, things that are easy for humans to just look outside and provide some ballpark estimate. There's also a very large population bias. Again, since most of these reports come from people, where the people are is where you tend to have more hail reports. So in parts of in the plains or in highly rural areas, it's much easier to miss, especially some of the bigger hailstones. So there have been numerous scientific field studies. These are often designed so that we can better characterize the size distribution of hailstones, the fall behavior, the hailstone characteristics, shape, density, lobe structure, et cetera. And as a result of some of these recent field projects, we do have an improved scientific understanding, and that could be used to improve how we're able to detect hail, which has implications for very short-term forecasts, such as severe weather warnings, as well as material damage. So scientific studies looking at how hail affects shingles, for example, and this is Ian Giambanco's group, IBHS, Matt Cumgen, others have worked with them on these impact-based astrometers. This also includes a high-speed hail imager, which I'll get to a little bit later in the presentation. But what we know about these science field campaigns is that we get a much better understanding of the distribution of hail, both in time and space. So for example, this is just one figure out of one of Scott Blair's papers. The Hailstone Field Project, which is one of the projects he's led, basically just used vehicles, and they drove around underneath and right behind hailstorms and tried to collect a much higher density time and space data set of how hail fell. So on the top is what is in the official record. This was a storm in southwestern Oklahoma in 2011, actually at the time produced the largest hailstone in the state. And we have a handful of reports, half a dozen here, to characterize a 2-hour window or an hour and a half window as this storm produced hail. And panel B on the bottom is what they collected with their field project. So again, a much better understanding, much better description, so to say, of the nature of the hail swath, which again is quasi-continuous in time and space. And because you're able to get a lot more observations when you do these science-based field campaigns, it's much more likely that you'll get the maximum hailstone size. So in some of these more well-studied storms, or these storms that go through highly populated areas, and you're much more likely statistically to have somebody pick up the biggest of the big hailstone. Whereas in very rural areas, when you're dealing with voluntary data collection by the general public, somebody to pick up a hailstone in their yard and call 911 or submit a report to the weather service, you're much less likely in that case to be able to pick up the largest hailstone. And that changes then kind of the climatology, especially of the very large hailstones. So in general, what we know over decades of research is that large hail, as seen on weather radar, is often associated with very high reflectivity. Typically ZDR close to 0, maybe a little bit above, maybe a little bit below, as well as some reduction in what we call correlation coefficient. So that gives us some information on, again, kind of the variability of the hail or the hydrometeor scattering characteristics within some volume of the atmosphere. And we've been able to design algorithms that can leverage all of these different products and the unique scattering characteristics of rain, heavy rain, light rain, hail, bugs, birds, tornado debris, et cetera, and what we call the HCA, which is hydrometeor classification algorithm. And in this 4-panel image here, this is from a hailstorm in 2015 in southwestern Oklahoma that produced a long-lived significant tornado. What we see in the lower right panel where we have red is where this algorithm is able to identify where hail is occurring. So in this case, again, it matches up where we have relatively high reflectivity or ZH in the upper left panel, a reduction in ρHV, which is the upper right panel where we see the greens and yellows, as well as ZDR that's relatively close to 0. I'll note for future reference here, this black star in basically the center of the panel is very low reflectivity. So generally in the 20s, maybe low 30s. This was where I was standing looking at the tornado to the southwest, and we were taking hail greater than baseball size. The algorithm, in this case, the hydrometeor classification algorithm, just identified this area as light to moderate rain. So it's like, why did this algorithm fail? How can we improve it to better detect some of these situations where we know we have giant hail falling? So we're generally at the end of the line for looking at how to improve hail algorithms on a local nature. So the hydrometeor classification takes all the radar data at one given point at each range gate and says, okay, what type of scatter is consistent with these combination of CDR, ρHV, reflectivity, specific differential phase, et cetera. There's some other hard rules that are applied, but tries to make a best guess, so to say, on what type of precipitation or non-precipitation would cause that. The problem is there's a lot of overlap. So again, in this case, the algorithm is saying we're really just going to see rain where the star is located. And that's largely because the reflectivity is just too low. This is lower than what we typically see for very large hail. And that leads to 2 ongoing research foci that I'm directly involved in. One is identifying hail in this kind of low reflectivity regime, where reflectivity is not particularly large. A lot of times in the WSR88D data, if we see reflectivity 65, 70 plus dBz, we would think, wow, that's got to be some really big hail in there. But what we see around supercells in particular is that you can get big hail at much lower reflectivity. And the algorithms, including mesh, tend to fail in those situations. We're also looking at identifying hail growth aloft using storm-based signatures. So not just saying, necessarily exactly where the big hail is falling, but trying to identify those storms which can produce the very, very large hail. And we've identified several signatures aloft in the mid to upper troposphere, mid to upper levels of these storms that seem to be associated with very, very large hail. But the underlying thing is we still need lots of observations to be able to develop and improve some of our radar-based hail algorithms. So this is some video from about the same time as that last 4 panel. And I don't really think we need a whole lot of the audio. This is in the high reflectivity kind of core region of the supercell north of the tornado. This was where reflectivity was 60 plus dBz, ZDR was relatively low. Everything here fits with what we would expect would be a big hail core. And there was at least baseball size, maybe larger, hail in this area. And this was, again, just due north of the tornado in southwestern Oklahoma. Where we were located, I was located northeast of the tornado, southeast of the hail core, and we were getting a very small number of very large hailstones. And in this case, there's a tornado in the background, but as the video slows here, you see some of these larger tennis ball plus size hailstones actually bounce through the field. There's one there that bounces at least 4 or 5 feet high. There's one that's going to be on the left side of the screen too that bounce. These are, considerably far in the field and bouncing up 4, 5, 6 feet from the ground level. These were very large hailstones, but again, the algorithm didn't do a good job identifying that there would be very large hail growing here. Just to get to the point of the kind of the official hail database and why we have issues sometimes identifying ways to improve the algorithm, which we need, of course, verification information for. These are all the hail reports associated with the storms in Oklahoma that day. There were other storms further northwest. And disappointingly, you see that there's really not a single, around the time of this storm, in the locations we were getting this, there's not a single hail report. There's one a little bit later, a little bit further east of golf ball size hail. But none of the baseball plus size hail that we know fell, because we have video of it, made it into the official database. So then further researchers in the future that pull these data and say, okay, this storm has really remarkable signatures, but look, in the hail reports, it didn't produce any giant hail. Whereas again, in reality, we know it did produce hail, and this is just one of the limitations of the public hail database. And that further drives the need to do some of these science-based field campaigns. So if we look at data aloft, we know what it looked like at the ground. But if we look further aloft, we see that this hail is falling in interesting areas. So if we look at this kind of bullseye, that's where I was located. That's where the second video looking southwest towards the tornado was. And we can see this kind of this weak echo region. I hope you're seeing my mouse on the screen to help point out these areas. But we were underneath this echo overhang. So this area on the east side of the supercell, the east side of the updraft, that had very high reflectivity, but not a whole lot of reflectivity was reaching the ground. In contrast to the west and to the north of the tornado, to the west of our location, that was underneath this area of very high reflectivity. Again, typically indicating the presence of a large amount or a substantial size of the hail that was seen there. And again, if we look at ZDR, we have this area of enhanced ZDR. This is what we call the ZDR column or the ZDR ring that was located to the southwest, kind of around where the tornado was located, which makes conceptual sense. The hail that fell in the two videos was located just to the north of that. We also see just west of this red bullseye. In the right panel is where we have these grays, kind of darker grays trending towards black, and this is highly negative ZDR. So we have positive ZDR associated with the updraft. This is raindrops that are being lofted in what we call the ZDR column, but being lofted in the relatively warm updraft. There's probably some mixed phase wet growth of hail occurring there too, but we do have this reservoir of highly negative ZDR. And if we look at ρHV, again, ρHV tells a similar story where we have this reduction in ρHV on the north side of the ZDR column, the north side of the weak echo region and bounded weak echo region, which is curious. And that said, okay, but let's look into quantitatively what's occurring here. What's the relationship between some of these signatures, like the negative ZDR and the reduction in ρHV on the left side of the bounded weak echo region, and hail size. So we have another case that was a 2016 case. This is a 2013 case that, again, record hailstone size in Oklahoma. As Matt would say, gargantuan hail, 6+ inch diameter, highly anomalous. Some of that really, really big hail fell, again, similar spot, northeast of the tornado, east-northeast of the main part of the updraft, as we can see in ZDR, where my mouse is pointing. We have a nice ZDR ring, ZDR column, reduction in ρHV, bounded weak echo region, all these signatures that tell us that this is where the updraft is likely located. And again, we see similar patterns of where the largest of the hail fell, which is relatively close to these mid-level updraft signatures. So this is just an animation. And again, we have the big El Reno tornado track. This is again from May 31, 2013. And north of that El Reno tornado track, we have some very prominent updraft signatures. So the right panel is at 6-degree elevation, that's several kilometers, 3, 4, 5, 6 kilometers above ground, where we see this area of high ZDR. This is the ZDR column again, indicating the presence of a strong convective storm updraft. If we go even higher than that, in the left panel is almost twice as high up at 10-degree elevation angle. We see highly negative ZDR. So typically, if we're in relatively small precipitation sizes, a highly negative ZDR would indicate that you have a general shape of a precipitation particle that's more vertical than horizontal. Whereas we wouldn't necessarily think that's the case for hail. We don't really know what hail looks like as it's growing in a supercell updraft, especially the really big stuff where it's getting impacted from below. But there's likely some what we would call resonance impacts, which I'll get to momentarily. So we're starting to look at some of these more experimental products, try to find some way that we could back out or automate the detection of some of these mid-level polarimetric signatures. So things that we're looking at include, for example, the minimum rho-HV close to a ZDR column. ZDR columns can be tricky to identify in big supercells. They're generally pretty prominent, but we've had a lot of issues trying to operationalize or come up with more of an operational algorithm for ZDR columns because there's a lot of sampling issues, especially once you get further away from the radar. We have big gaps in the radar beam and gaps of the atmosphere where we don't sample, and that complicates how well we can resolve ZDR columns. But we're looking at things like, what's the lowest rho-HV close to the updraft? How does that correlate with hail size? What's the average ZDR, or what's the minimum ZDR? Can we establish some good relationship between the lowest rho-HV and the lowest negative ZDR and hail size? And we're seeing some interesting results from this, even though we're kind of in the early stages of it. We've looked at more than a dozen storms so far. So this is just a spattering of 30-minute accumulated minimum rho-HV at very cold temperatures, -30, -40 degrees Celsius, and minimum ZDR. Minimum ZDR is on the bottom, minimum rho-HV is on top, and these all are 3 storm cases that produce gigantic hail, exceeding 4 inches, some case 5, 6-inch hail. And again, similar things that we see, there's very large reduction in rho-HV, generally co-located with highly negative ZDR, where we're seeing ZDR of -1, -2, and all the algorithms fail there because they don't expect hail or really any hydrometeors to fit that combination of ZDR, rho-HV, KDP very well at all. So I alluded to this earlier, but we've looked at, with Arthur With, he's kind of leading the data analysis part of this right now, but looked at 30 cases of 4.5+ inch hail, so 11.5 centimeters and larger. And looking at things like the existing commonly used algorithms like MESH, maximum estimated size of hail, that's just based on reflectivity. And we've long ago probably reached the limit of how we can use reflectivity, at least the magnitude of it alone, to identify hail. He's also looked at mid-level rotational velocity, storm top divergence. So these are things that we get from the velocity data that give us some indication of supercell intensity in the case of MRV, and we know that a lot of the biggest hail is produced by supercells, and storm top divergence, which is again a proxy for updraft intensity. And by far, out of those kind of 3 traditional hail size indicators, the storm top divergence and mid-level rotational velocity have the best correlation in the cases that we've examined so far. But adding these mid-level signatures, in this case, I've included in this chart minimum rho-HV at -40 and minimum ZDR at -30 degrees Celsius, we see actually even better correlation with hail size. So this gives us some confidence that as we continue to identify cases and examine more data, expand the data set, that we may be able to really leverage these mid-level polarimetric signatures to give us improved estimates on which storms will produce the biggest hail. We also, speaking of where hail falls relative to updrafts, and that kind of speaks to the importance of being able to first identify the location and the intensity of updrafts in radar. Lauren Pounds has looked at this quite a bit. This is some of the work that she presented at the Severe Storms Conference last fall, basically initiating a bunch of trajectories in a supercell that was simulated at very high resolution, using data from 2012, which was a supercell that produced very extremely large hail northwest of Oklahoma City in central Oklahoma. And what she had noted, the results from her work, is that the largest of the hail falls very close to the updraft. And conceptually, this makes sense. We have an updraft that is 50, 60, 70 plus meter per second peak velocities, the only thing that will be able to fall through that are hydrometers with very, very high terminal fall velocities. Anything with a fall velocity less than the updraft is, in a ground sense, going to get lofted upward. So as you get towards the end of the edge of the updraft, where perhaps vertical velocities decrease to 20, 30, 40 meters per second, again, still robust, but you do have hail, very large hailstones that are going to be able to make progress towards the ground. There will be a ground relative downward motion on those hailstones, whereas the smaller hailstones with smaller terminal fall velocities will get advected by the wind through what we would call it a psi sorting mechanism and move further into the forward flank updraft. So in this case, this is on the right, a vertical cross section through the simulated supercell, showing on the top panel the number of melted hailstones, the sub-severe hailstones in the middle panel, and the bottom are the severe hailstones. So how many of the 1+ inch hailstones make it? And as we go from the fully melted to the sub-severe hail to the severe hail, we're getting closer and closer to the updraft. And the result of that, if you integrate that forward in time and look at a swath, this is a hail swath. And again, this is much more akin to what happens in nature. We have this kind of quasi-continuous area of hailfall, whereas in this case, our individual hail reports are where the numbers are located. We're only getting very small snapshots in time and space if we look at the report database. And in this particular simulation, and again, this is consistent with conceptual models, but the largest hailstones are located along kind of the inflow side or the south side of the hail swath. And the very structure of this leads to the conclusion that this is likely psi sorting occurring. Again, the smaller hailstones that fall more slowly get moved off away from the updraft more quickly. So again, another project Arthur Witt has looked at, independent of Lauren Pounds' work, is looking at a bunch of cases so far, 13 events, 185 severe hailstones, 110 6 severe hailstones, and trying to put where those occur relative, where those reports are occurring relative to updrafts. And what he's found is that as you get towards the larger sizes, 1, 2, 3+ inch, you get closer to the updraft on average. So for example, the 7.5 centimeter and larger hailstones are centered on average in these 13 cases 7 to 8 kilometers away from the center of the updraft. And the smaller hailstones, 2.5 to 5 centimeter hailstones, are at the 90th percentile, are occurring at 11 to 12 kilometers away from the updraft. So we can use this to inform, ideally, hail algorithms to say, okay, even for the same combination of ZDR, ROHV, the radar parameters, as we get closer to the updraft, we would expect more likelihood of seeing this very large hail. Again, especially the largest of the large stuff. So we can look at hail reports. That's great. There's lots of issues with the hail report database, time, space, et cetera. I've talked about that. And that leads us to try to simulate hailstones. So what if we have a group of hailstones, what would it look like to a radar? That way we don't necessarily have to rely on correlation studies between reports and observations from radar. We can look at simulating these hailstones. For small hail, we can use Rayleigh equations, relatively simple. As we go up to larger hailstone sizes, and that's relative to the wavelength of the radar, we have to change to more rigorous numerical methods of estimating the scattering characteristics of hail. A common way to do that is to assume hail is some spheroid or maybe ellipsoid, but generally spheroid has been historically used as a model for hail using a T-matrix method, or there's other methods to do it. And when we do that, we see, especially for wet hailstones, like a panel on the upper right here is hailstone volume diameter increases left to right, showing ZDR. And we can see some very large fluctuations, rapid fluctuations in differential reflectivity over very small changes in particle diameter. Again, especially as we get up towards the higher frequencies of C-band, X-band. Very complicated behavior then between the shape and the size of the hailstone and what we get back from the radar. And those were just using smooth hailstones. As we go to more realistic looking hailstone shapes, this is some work that Georgia Makarovich, colleague here, and several others in this team have looked at, but basically trying to model the radar characteristics of rough hail. So we know that not all hail, oftentimes hail isn't perfectly smooth. There's protuberances, et cetera, on it. And these protuberances and how rough the hailstone is can have significant impacts on what it looks like to a radar. Similarly, this was other work done by the PSU group, Jing and Matt and others, using data collected from the IBHS field campaign that went out in the field, collected giant hailstones, 3D scanned them, and with that, then you can numerically simulate what these look like. And the panel on the right, as you go top to bottom, you get different hailstones, different individual hailstones, and different products that are located in different columns. The gist is that sometimes, as a function of look angle, hailstones look relatively similar depending on how you're looking at them. There's other hailstones where the scattering characteristics of the hail changes massively depending on specifically how it's oriented towards a simulated radar. We also have issues then if we're trying to simulate a population of hail. If we want to know, like, for example, how would ZDR look, we have to know how it's falling and exactly how it's tumbling, if it's random orientation, if there's some mean angle towards it, if there's some tumbling about some mean angle, that can affect, again, very significantly how the radar looks. So I'll just say, since I need to speed up quite a bit, is that how you simulate a hailstorm in a model depends on a lot of things, including a lot of stuff that the model doesn't give you. So mass composition, for example, shape, fall behavior, and a whole lot of other stuff. So to get a handle on this, we want to take photographs. We want to be able to see how hail falls. And there have been a couple of efforts at this. This Matson and Huggins, most of this is work that occurred in the 70s and 80s using either mirrors or multiple cameras. This was generally focused on photographing smaller hail as it fell. So basically, again, trying to get some handle on the canting angle or the fall behavior of the hailstones, because that affects how the hail looks like to a radar. So it was just another study, Beeman and Lazowski, again, setting up multiple cameras, multiple mirrors to try to see if it's possible to get multiple exposures of a hailstone as it falls, and from that, can you back out some sort of statistical distribution of hailstone canting angles. Both these generally use stroboscopic photography. It's hard to get the frame rate, especially for the larger hailstones, sufficient enough that you can sample them many times as they fall through some volume. But the theory behind this is that if we have multiple cameras, we know that the imaging characteristics of the sensor, or in the older cases, the film, the lens, we know the distances, we know the angle between the cameras and the distances. We can get some good estimate on where the hail is, the size of it, and be able to place it in some volume. So the overarching questions for this project, as I turn more towards the hail imager, this new novel measurement system, is can we obtain better estimates of hail PSDs? So we don't want to just pick out the largest hail. We want to know how much of that large hail is there versus smaller hail, et cetera. what do the large hailstones in particular look like as they fall? Again, past studies have looked at generally the small hail, 1 inch or less, occasionally a little bit more, but we know very little about the actual in nature fall behavior of the very large hailstones. There's been some wind tunnel studies that generally look at hailstones on the order of a few seconds. It's hard to keep a kind of a simulated hailstone model stable within the wind stream of a wind tunnel. So what we want to do is try to quantify canting angle distributions, water distribution. So how exactly is the water distributed on a hailstone that could very significantly impact what it looks like to a radar? And we want to be able to see if we can see these very delicate structures on hailstones that might not survive impact on the ground. So again, a lot of hailstones that fall that are reported are falling off the ground, they're collected, they've been beaten up, they've been melted, again, had an impact with the ground. We don't necessarily know what changed between when it was in the air and when it was in the ground. And ultimately, again, we want to be able to use these to improve our radar-based hail algorithms. So there's lots of gives and take when we look at imaging, taking photographs, video of very large hail. So very large hail tends to be sparse. And that means we need to sample a large volume statistically to be able to get some hail to fall through the volume. Large hail tends to have very high fall speeds, which means we need to sample quickly. We can't sample once a second. Chances are a big hailstone is going to fall through that completely. And potentially very intricate structures that we want to be able to image, which means we need high resolution. So we need to sample a large volume, high resolution as quickly as possible. Kyle Ortega was great getting funding and kind of spearheading the version 1 of this hail imager, which used just about 12.5 megapixel machine vision cameras and NVIDIA Jetson development kit. It generally worked at 15 to 18 frames per second. And Kyle, Sean, and I sat down and said, okay, what can we do with this? Part of it was speccing out the equipment, and some of that was limited by the funding. Again, this was kind of prototype, but it was essentially the goal behind it was to get a lot of light in a volume, take a high-speed camera, and see what we can see. Can we see hail falling naturally? And what we learned from that is that we do 12.5 megapixels with the lenses used is high enough to be able to see some fascinating structures. So we can see lobe structures in hail as it falls. We can see raindrop hailstone collisions. We can see water toruses on melting hail. A lot of this, has been observed in laboratory settings or theorized, but not many actual observations in the field in nature of some of this stuff occurring. But what we realized was that the computer was much too slow for real-time processing, and the frame rate was too low. So as we get to bigger and bigger hail, we have more problems. So I talked a little bit about it previously in terms of having to sample a large volume just from a statistical standpoint, because the largest hail is so few in number. It's very low density in space. There's not many of them. It's a long-winded way of saying that. And that very large hail can fall very quickly, 20, 30, 40, up to 50 meters per second at near sea level pressures. So if we want to be able to capture how that falls or how it's tumbling, how it's moving with time, we need to get images very, very quickly. So at least on the order of hundreds of frames per second, which is a problem for data management and real-time processing, et cetera. So again, if we want to focus on the big stuff, which has bigger fall speeds, we need to capture an even larger area. We need to maintain the very high resolution, and we need to be able to do it very, very quickly. And that required faster camera, faster computer, faster everything. So that led to version 2 of the hail imager. So this was truck mounted, and it was truck mounted so that we could drive it underneath a hail core or ahead of it, let the hail core move by, then drive out away, get in position again. We really get to maximize the number of deployments on a given hailstorm. Also attached to this is a full meteorological mobile mesonet instrument package. So we're getting temperature, wind information, pressure, humidity, et cetera, that can be matched up with the hail data. And because it's on a truck, we then also have sufficient power. for the computer and for the other equipment. It doesn't need to be battery operated like the first version was. So for this version 2, we moved up to 330 frame per second cameras, and we have 2 of them now. Generally pointed rearward at approximately 30 to 60 degree angle. We've played around with that as the project went on. We realized early we need a lot of light. That's a very short, we're using very short shutter speeds, very short exposure time. Out in the field, we want a large depth of field, so smaller apertures on the lenses. We need a lot of light. And in fact, we realized that even the 70,000 lumens we have now in the back of the truck is insufficient, and we're adding more lights for coming field deployments. There's also a much more capable computer. A lot of stuff is done on the GPU, being able to read the data as it comes in, do some preliminary processing, and record it out. And that can happen actually in real time at these very high frame rates. So Kyle led field deployments with this last spring and summer, and was able to capture some really great data in some really interesting hailstorms. So in this case, what we have here is an animation. This is approximately 300 frames per second of some very complicated microphysical behaviors. So one of the first things that we might look at, for example, is this large hailstone that's falling from the upper left down towards the center right. It kind of looks like there's a water torus around it, but it's not a horizontally oriented water torus because the stone isn't falling straight down. The stone is falling at an angle, and so the water torus gets displaced at an angle. We also see that this camera is capable of picking up raindrop breakup. For example, we kind of have a bag-like breakup occurring in the center of this image, and I'll wait for it to loop here. As you see a very large raindrop start to expand in a bag-like fashion before it splits up. Towards the bottom, and I'll let this go, you can see with my mouse, hopefully the image or the video is clear enough here. We have a melting hailstone. All the ice is at the bottom. There's a very large area of trailing shedding drops behind it. This is not a small water torus shedding off a couple of small drops on the side. This is a very long area of melt water stuck behind it and trailing behind it. And these are things that, again, we don't model this in forward operators. We don't model it numerically. But this is stuff that occurs in nature, much more complicated behaviors. So another example, this was getting a little bit more to...
Question?
Yes, go ahead.
In that previous loop, do you have any sense of the dimensions of those particles?
So at this time, we haven't done the analysis on this particular case to match up, to provide some distance from each of the cameras. That is left to future work. This was just kind of a preliminary data grab, so to say, from one of the cameras. But yeah, since we have the 2 cameras looking at different angles, we can use ray tracing, which I'll explain momentarily, to place these things within some 3-dimensional volume as it falls, and then from that we can get some size estimate.
Thank you.
So here's another example. This is not really highly melted hail. So this is this hail that looks much different. We don't have a water torus necessarily around it. There's actually quite a few hailstones falling in this image. But what we do see is very rapid tumbling behavior. This is one hailstone in particular that starts in the upper left corner and falls down towards the center bottom. There's kind of an exploded contrast enhanced view on the right side. This hailstone is rotating at about 50 hertz. So 50 times a second, we're doing just about a full evolution. I mean, for all intents and purposes, we would say this is, full tumbling behavior, kind of a random orientation. You do see other hailstones, though, that look a little bit more stable. And there's one that comes in towards the end of this loop at the top center and ends just about where my mouse is. That does look like it has a more stable orientation, mainly aligned in the horizontal. So even within this one, we don't have not all the hailstones that are being sampled are behaving the same way. Not all hailstones look anything like a sphere, even in free fall. So this is an example of 1/20th of a second of data as this hailstone fell. And this hailstone doesn't look anything, again, like a sphere or an ellipsoid. It is very asymmetric. It is as a very high aspect ratio, 3:1, 4:1, 5:1, more stably oriented in the vertical. And as it falls here in this, again, we're only looking at 1/20th of a second. It's stable, relatively stable in the vertical, but it's rotating about that vertical axis at greater than 50 hertz. So again, another really neat example of something that, if this hailstone falls, a lot of these hailstones, when they hit the ground, just shatter. So it's like if you're collecting data if you're collecting hailstones off the ground to study them, you're never going to be able to see this because this in this case, this hailstone completely broke up when it smashed into the ground. So another example here. This is another example of drop breakup. We have quite a few of very large raindrops, probably melted hail, fully melted hail, breaking up. So on the right side, I kind of pulled out some individual frames from this towards the early part of this short little loop. We have a very horizontally aligned, very high aspect ratio in terms of H to V. So low aspect ratio if it's V over H. Very wide raindrop here, fully melted. We get this bag-like breakup where it blows up in the middle of the drop. And again, what this would look like to a radar, I don't have any clue. This is very, very interesting behavior. And then eventually, owing to surface tension and drag effects, that completely breaks up. And we end up with this distribution of much smaller raindrops. But again, not randomly oriented in space, randomly distributed. This is, of course, coming from a single raindrop breakup. And the hope is that we can get statistics actually on the distribution of the raindrops that result from some of these individual raindrop breakups. So if we start off with an 8 or 10 millimeter raindrop, especially as you get to the 10, that's not going to be stable. That drop is going to break up. But we're hoping to be able to put numbers on, what size of drops are we getting from this individual raindrop breakup. So again, just getting into kind of the stereographic nature of this effort to image hail. We have two cameras, again, slightly pointed at different angles. And as a result of that, we're capturing different parts of hailstones or the same hailstone, but looking at different viewing angles. So this is just one example from the two cameras, the left camera and right camera. And as expected, for a non-perfectly symmetric spherical particle, it looks different. And if we were to take one image of this, we might say the image on the right looks kind of spherical. The image on the left does not look spherical. It's very loby. We're seeing a different part of the hailstone just by random orientation of it. That would be expected to have a more complicated scattering behavior. So just kind of, our cartoonish diagram here, if we have two cameras, we want to find the line that connects each camera to the center of each hailstone. We can locate the hailstone in three-dimensional space using relatively simple geometry. And if we know the distance between the hailstone and the camera and the characteristics of the camera with the lens, we can convert this pixel coverage to an area. So that will get us some estimate on horizontal dimensions. So again, just taking the same image, it's some rudimentary or very elementary size estimates, we're able to get the minimum axis, the major axis. We're able to remove some of the impacts of spikes and just generally get a pretty good idea on the shape of this hailstone. And if we do that over a bunch of images, as we're able to sample this as it falls, then we can get essentially trajectories of some of these individual hailstones. And we could get fall speed behavior and horizontal motion. And if we know that the full three-dimensional fall or the three-dimensional motion vector, then we could study, for example, why is water distributed on a hailstone like it is? You know, we typically think if a hailstone falls straight through, there's no horizontal motion. It's just falling straight in a windless regime. You're going to get a water torus around the edge of it. And that's going to typically enhance ZVR until we get bigger, and then we get much more complicated behaviors. But on some of these, it could fall at almost a 45-degree angle. So it comes out of the storm. The wind at the ground can be strong. There's other reasons. But that, again, shifts where the water torus is oriented. And now maybe you don't have a water torus oriented in the horizontal, but maybe it's at 45 degrees. And as this happens, the stone might be tumbling. So now you have a water torus that's being impacted by not just a vertical wind, but a horizontal wind, and the stone is moving, and again, very complicated behaviors. But what we're starting to do with this is to look at some of these hail deployments with radar data. So basically saying, okay, we know what the hail looked like as it was falling, and we have data over the probe. For the next couple of years, the goal is to get data over research radars, so mobile radars, or if we can get some good cases in central Oklahoma, we have access to a NSSL owned operated WSR-88T, and we could actually do true RHIs over the probe, so we can get very high resolution radar data of the hail as it falls. And from that, we fully expect to be able to improve some of our hail algorithms. In this case, again, not only did the radar data change, or some of the signatures change as it moved over, but the hail itself varied massively from the front of the storm to the core area of the storm to the backside of the storm. There's very distinct changes and variability in the nature of the hailstones. So if you look at, for example, this case in South Dakota from last year, early in this particular deployment, it was a very sparse number of mostly smooth and oblate hailstones, but that transitioned to large hail, in this case 2¼ inch approximately, with very prominent lobes and asymmetries. So we can see, you know, the upper left hailstone kind of ish looks quasi-spherical or ellipsoidal. We have other things like the lower left image and the lower right image, where we definitely look like there's some accretion, freezing, much more complicated structures, lobey structures, and not necessarily spiky lobes, but lobes like there were collisions with other small hailstones or other not fully liquid hydrometeors as the stone was freezing. And we end up with, like the case of the lower right, where you have one large hailstone and it sure looks like a couple of smaller hailstones that's got stuck to it as it's tumbling around. Approximately 2 to 5 minutes later, the nature of the hail changed completely, and it went to much more spherical hail, much smoother, much fewer prominent lobes and asymmetries. Some of these hailstones had fully developed water toruses and some indication of shedding. Others did not. So again, a very huge range of characteristics of these hailstones. And then not 1 or 2 minutes later, it was back to more aspherical hailstones. So the fact that the nature and the structure and the physical characteristics of this hail changed so quickly tells us that aloft microphysically, different behaviors were occurring, and we were in different microphysical regimes for growth of this hail. And I'll note towards the end of, again, this particular deployment, we had another very strange hailstone that had very atypical aspect ratios. This was very vertically oriented. It was a 3-to-1, 4-to-1, almost 5-to-1 aspect ratio. In this case, it actually almost looks like a human figurine that was falling. And as it was falling, it too was kind of twirling about some vertical axis. So again, really wild. And some of this probably explains why we have difficulties matching up sometimes maximum hail size reports with the radar data. So I know I'm essentially out of time, so I'll just leave this slide up in terms of some of the future work. A lot of what we have left in the future, we're comfortable with the equipment and the system itself. So a lot of it now comes down to the work of actually doing the analysis. And we think we have enough very unique data that we can combine it with the radar data and to be able to make improvements on how we're able to detect and provide short-term forecasts. And again, I would love to talk about or field any questions about forward operators or maybe numerical weather prediction estimates of this. But since I'm at almost an hour, I'll close it up and take any questions.
All right, great. Thanks, Jeff. That was wonderful. Boy, this is a tough topic. So if anybody has any questions, you can just raise your hands within the Zoom, or you can just talk. That's fine as well. I know I have a few questions, so I guess I can start. So going back to the first part of your talk with the radar and the work that you've done with the negative ZDR and the low rho HV for the 4.5-inch hailstones, that seems somewhat promising and maybe at odds with some of the talks we heard that the future is bleak for using radar to estimate hail sizes. So have you guys looked at whether there would, using the negative ZDR and the very low correlation coefficient, whether that would lead to large false alarms for hail that's less than 4.5 inches. So in other words, you only looked at 4.5 inch and larger, right?
Yeah. So this is an ongoing project. And what Arthur and I did was start at the big stuff. What we're currently doing now is collecting data from the 2.5 to 5 centimeter, so 1 to 2 inch, to contrast with that. Because one of the we see very prominent mid-level signatures aloft in these giant hail producing storms. We occasionally see similar signatures in severe hail producing storms. So not necessarily the ones that produce this giant stuff, but hailstorms that may produce only 1 2-inch hail. But they certainly seem more prominent in storms that produce this really big stuff. So yeah, this is a work in progress. I don't really have a great answer for that. I've looked at enough cases to know that, it certainly isn't unique to storms that produce, gargantuan size hail, 4.5+ inch. But it certainly seems to be much more common.
Okay.
Especially when you combine it with some of these other kinematic, storm top divergence. This is all kind of getting at the fact that can we identify which storms will produce this biggest hail? And how can we leverage the polarimetric information, these mid-level polarimetric signatures, with some of these more traditional kinematic signatures, stuff like storm top divergence, which again is just really a proxy for updraft intensity.
Mariko, go ahead.
Hi, Jeff. Thank
Hi.
you for the fun talk. I have 2 questions. One is about the updraft. You mentioned some relationships between the updraft and hail detections. How did you estimate the updraft? Did you use a multi-Doppler or just estimated from single Doppler measurement?
Yes. Yeah, so all of these were done subjectively. This is a manual analysis. So it's basically going through and looking at every scan and looking at all the available information that we have. This is generally single pole because we're using operational WSR88 data to do this.
I see.
So it's looking for things like boundary Wicaca regions, low-level convergence signatures at the base of updrafts,
Okay.
upper-level divergence signatures that would, kinematically for mass continuity would be expected to be on top of updrafts. ZDR columns, those kind of collection of traditional radar signatures for identifying updraft location.
Oh, okay. Okay. Second question is about the reduction, the signature of reduction of GDR and ROSV. You showed some simulation examples. Actually, what is the cause of the reduction of GDR and ROSV? It is because of the shape of particle, shape of hairs, like orientation and or irregular shapes, or non-radial scattering, or other we should consider about the debris.
Yeah, so some of this is all of the above. Once you get, as you know, the larger sizes, so what that is depends on the radar frequency or the radar wavelength on, you know, when this starts to become an issue. But we transition out of the regime where the Rayleigh approximation is good to where we get significant resonance effects.
Okay. Mm-hmm.
And that is really where we really lose our relationships between, for example, hail size and the scattering characteristics.
Mm-hmm.
So the
Okay.
scattering amplitudes.
Yeah, makes more sense.
Yeah, so that gets really complicated. And again, some of the hailstones that we get, and the IBHS group has seen this, and we saw it in some of the radar deployments that were imaged, or in some of the hail imager deployments. We do sometimes get very smooth hailstones that look relatively spherical. If we use spherical models for the hailstones in simulating what the radar characteristics would be, you know, there's not a whole lot of error there.
Yeah,
we have
I
other
understand.
hailstones that are much more exotic. I mean, nature laughs at our simple models. You know, even if we go from spheroid to ellipsoid, you know, we add another dimension of variability. You know, there's still laughably bad models sometimes. And we see that in a lot of microphysical regimes. We certainly see that when we look at hail.
Okay, thank you.
Go ahead, Steve.
Yeah, hi again, Jeff. Steve Schwartz here.
Hi.
Hi. I just really want to compliment you on the use of the photography, the imaging, the video that's coming out of that. I think that's a great technique. And it's, I think, really underexploited. And looks like you're kind of pushing the boundaries on that in terms of resolution and lighting and so forth. So I really want to compliment you on that. That's really all my comment.
Oh, thank you. I appreciate the kind words. This is an exciting, it's not a particularly high budget project. You know, certainly compared to other meteorological instrumentation, we were able to put this together for lower to mid four figures. So I only mention that because there might be resources available elsewhere in the community to build out similar imaging packages. And again, you know, you would tailor your selection of hardware, camera lenses, et cetera, for what you want to sample. We wanted to sample the big hail because that's been unsampled so far in scientific literature, at least in the field. But you know, you could apply this. We could run the same imager for winter storms where we get big giant aggregates and look at the fall behavior of giant dendrite aggregates.
Yeah, I think in some sense the interpretation lags the technology. The technology is there, but it's a question of doing it and then interpreting it. We did a project some years ago using high resolution photography to look at clouds, and we used LiDAR to get the distance so we could translate pixels into dimension. And we had resolution at a kilometer. We had resolution of about a centimeter. So, and there's structure there at that level. So it's totally unexploited. And, you know, what the satellite sees is tens of meters at best, and just a lot of structure there. So I think there's a lot that could be done. Yeah,
ideally, my ultimate kind of moonshot for this is to try to get something up in the wet growth region of supercells. You know, we have some armored aircraft penetrations of supercell updrafts. For obvious reasons, you know, that's very, very difficult to do, to, you know, get scientific instrumentation into very inhospitable areas of supercells where this very large hail may grow. Safety reasons, all sorts of things. So ultimately, I'd like to find some way to scale this down a little bit and get it balloon borne, kite borne, something so that we can get images to see, where we're seeing this very low ZDR and very low rho HV. What does it look like? We don't really have a good understanding of what this would be in 30, 40, 50, 60 meter per second updraft, where you might have, a baseball sized hailstone that's getting bombarded relentlessly from the bottom because it's just, steady state in the updraft. And it's just getting, I don't know. And we don't know necessarily how stable such a hailstone would be. Would it be tumbling and you'd get, more regular growth on it, or would you get really exotic growth behaviors that might melt or come apart? Yeah, I don't know.
I think those hailstones will shred your balloon.
Yeah, well, that's an issue. Yeah.
All right, great. Thank you. Jeff, just one more real quick question. You said you wanted the camera to be real time. Is that just to check that it's working, or is there some other benefit to having the data right in front of you in real time?
Yeah, I think a lot of it is just to ensure everything's working. And some of it is there was version 1, it took a long time to process the data. So you collect the data and it would take hours and hours to get images out of it. So when it comes to things, ensuring that the lenses are set correctly, everything else, just kind of the logistical nature of some of the issues that might come up with in-field equipment use. Being able to see everything real time would certainly helps troubleshoot and make sure we don't have unexpected issues.
Well, so thanks again. This was really, really great, and I think gave everyone a sense of what hail research is like and why some of us may avoid it. But really appreciate your time today, Jeff, and I'll be catching up with you hopefully soon. So
We'll do. Thanks, Mike. Thanks for everybody else for stopping by. Sorry I went long.
That's okay. That's okay. It's a nice part of the online.
Exactly. You can just peace out and nobody.
Yeah.